This is a Module 1 video on stereoselective elimination. One of the advantages of bimolecular elimination reactions is that they can be highly stereoselective, and the mechanism is stereospecific. Please review the terms stereoselective and stereospecific, as well as diastereomer from Chem 202Z, if you're not absolutely certain what those terms mean. In work from the 1950s, the rate constants were measured for each of the bromide diastereomers, and on your own you should determine which one is RS and which one is SS. And these were treated with two slightly different alkoxide bases. The first two entries are sodium ethoxide in ethanol, and the third and fourth entries are sodium tertiary butoxide in tert-butanol. The evidence is the stereochemistry of the alkene structures, and you should review the appropriate terminology for the stereochemistry of each alkene product. Additional evidence is in the table, and it is primarily the rate constant. The yields are similar, and the concentrations of the alkoxide are similar, but the nature of the alkoxides are different. Looking to Part A on the worksheet, you're asked to write in the substituents on Newman projections for each of these alkenes. To review from last semester, for a Newman projection, looking at two adjacent chiral centers, I recommend orienting yourself looking along the axis of the bond between the two chiral centers. I'll show the bottom part of this page, and we'll do the first set of Newman projections together. Looking down the axis between the two chiral centers with the phenyl group at my feet, for the chiral center closest to me, the methyl group is on the right and the hydrogen is on the left. For the more distant chiral center, with the phenyl group pointing up, the bromide is to the right and hydrogen to the left. This is a staggered conformation, but there are two other staggered conformations. Keep the orientation of one of the chiral centers the same in all three conformers, and so I'll draw those in for the second and third Newman projections. Then for the chiral center in back, we'll be a little bit more careful about that. But in going from the first structure to the second structure, the phenyl group has moved in a 120-degree rotation to this position, which means that the bromine is also moved 120 degrees in the same direction, and then hydrogen is here. And then another 120-degree rotation puts bromine here and hydrogen at this position. On your own, do this for the other diastereomer. Now for the claim, proposing a mechanism for elimination, the textbook makes a claim, And I will recommend that you adopt that claim and test that on the structures of these two diastereomers, considering all three of the staggered conformers. Then going to the last page of the worksheet, consider all of the evidence that is provided. There is information on the stereochemistry of the alkene structure, but there are also rate constants for the two diastereomers and rate constants measured for reactions with sodium ethoxide and with sodium tert butoxide. And that additional information may help you with the reasoning that links the claim with the evidence. This concludes the Module 1 worksheet and video on bimolecular elimination.